So thank you very much for the kind invitation and also for accommodating my needs yesterday. I was a bit jet lagged in the evening. That's why I backed out of asking another question that would take us into another big discussion. But thank you anyway for that. That was kind. Okay, so I'm wide awake today now. It's much better. Okay, so you know, the biggest room in the world is the room for improvement. And that's what we want to talk about today, or I'm going to show you a few topics maybe where there's room for improvement. I think it's important to understand the challenge, because if we have a good understanding of what the problems are, it helps us identify good solutions. Solutions that won't become tomorrow's problems. And I realize that my role in this is probably the easiest. I don't have to enforce regulations. I don't have to write regulations. I don't have to test if products that are being put on the market are really safe and comply with regulations. I'm a scientist, and I can take the 10,000 feet perspective and look at where the challenges are in the theory, not in the practical world. So if you allow me to show you my perspective, which is that perspective, it's clearly not the practical perspective. You can maybe look at me as like a science jester or something like that. I will humor you, maybe I'll annoy you a little bit, but I will give you some of the facts as we see them right now. Okay, so just to be clear on the terms, I'm using these terms. So we all know what a food contact article is. It's the finished packaging, it's the conveyor belt, it's the tubing. It's the article that is intended to come in contact with food. Oftentimes, this term is mixed up with food contact material. The materials are actually the materials that are used to make a food contact article. Food contact articles can consist of many different materials. So I'm going to try and be precise and use food contact article when that's what I mean. But what I'm going to be talking about mostly are food contact chemicals, and these are the chemical components of food contact materials and food contact articles. That's what we're interested in. We're interested in understanding, do they pose a health risk to humans or not? So we've all heard a lot about migration already, and Christina Nerin did a beautiful introduction on that topic just before, so I don't need to explain to you. Maybe one aspect that could be relevant is that there's also a reverse process of this chemical partitioning, which is, I think, known in FDA circles as flavor scalping, when food chemicals are taken up by the packaging material or by the food contact article. And that is something to keep in mind when we're talking about recycling. That's an important aspect for recycling. And you all know what the parameters are: heat, storage time, chemistry of the food stuff, of the packaging, but also the packaging size actually will determine levels of migrants in food. So if you have a cube and you shrink the cube, you're increasing your surface to volume ratio. So that means smaller food packaging potentially has relative higher migration levels than big bulk food packaging. Okay, so let's take a look at the European perspective. I will try to be, I'll stay on that side of the Atlantic, maybe that's a bit less provocative. So this is a slide that I'm taking from Gregor McCombie, who's a Swiss enforcement officer. Some of his work actually was mentioned just before by Dr. Curidan. And he presented this at last year's September stakeholder event at the European Commission. So you may know that the European Commission currently is in the process of reviewing food contact regulations. And Dr. McCombie was asked to give the perspective of enforcement, and this is what he said. So he said, potentially, we're dealing with 100,000 migrating substances. How does he derive that number? Well, he says there's about 10,000 listed substances, and each of those listed substances can have an additional 4 to 6 to 10 impurities, reaction byproducts, breakdown products, and so on. Because we're not dealing with pharmaceutically pure chemicals when we make food packaging, right? There are impurities in there, and I think some of the talks we heard yesterday illustrated that quite well. So 100,000 potentially migrating substances, 10,000 of those are used as intentionally added substances. Then specifically regulated in Europe are about 1,000, and that applies to the plastic food contact materials because the other food contact materials are not harmonized in Europe. There are regulations for those on the national member state level, but European-wide it's the 938 substances in the plastic regulation. And then the really important part is what is actually effectively controlled. How many chemicals are being enforced? And there, depending on which member state country you ask, it will range from less than 10 to maybe 100 chemicals. Okay, so what? The dose makes the poison. That's the famous misquote by Paracelsus, because he actually didn't say that. He says only the dose determines if a thing is a poison or not. Everything is a poison. And good, now it's working. Thanks, Neil. I live really close to the place he was born. It's like 20 kilometers or so out of Zurich, where I live. And this is Eck by Einsiedeln. So once I went there, it was a rainy day, and I took a picture of this memorial, his birthstone. Paracelsus was born here, 1493. Paracelsus was definitely a thought leader, and I'm not saying that the dose doesn't make the poison. It definitely does. We know that if you drink 18 liters of water within 1 hour, you will drop dead. The water is an overdose, it kills you. No question about that. Paracelsus studied acute toxicity, right? And what we're dealing with now is a different beast. We're dealing with low-dose, chronic daily exposures over the whole lifetime, and the lifetime starts pre-conception. It starts before the oocyte is fertilized by sperm. It's the fetus that's being exposed. It's the newborn, the infants, children going through puberty with lots of hormonal changes. Then maybe pregnancy again later in life, old age. So that's the job we have to do to assess whether chemicals are safe throughout the whole lifetime. And I will give you two challenges here. The first, this is a dose response curve, typical dose response curve. This is a study in rodents, male rodents, given DHP, one of the phthalates that we heard about orally. And there you can see this is quite nicely confirming to the dose makes the poison. So on the y-axis, you have the endpoint, which in this case was anogenital distance. It's an anti-androgenic endpoint. And on the x-axis, you have the increasing dose. And you can see the control, the first dose, no statistically significant difference, and then a kind of something's happening there. So as we increase the dose, we get a response. The dose makes the poison, okay? Same study, different endpoints. We're all over the place. This is what we call the non-monotonic dose response. So we're looking at different endpoints in the same study with the same doses, same chemical, and so on. And this is a challenge. This is a real challenge. And if you haven't seen it, Denmark just a couple of weeks ago published a report on how to deal with EDCs, endocrine disrupting chemicals that have these non-monotonic dose responses in risk assessment. And I've got the reference there. They've come up with a practical, workable solution to that. Other second challenge, mixture toxicity. It's been mentioned a few times already. Or known at EPA as the new math. What does it mean? So what are we doing right now? We are taking one substance at a time. We're looking at one substance by substance by substance. We're setting the acceptable daily intake for each of the substance, and we're assuming that there's independent action. All these chemicals have no interference whatsoever with each other. And so regardless how many chemicals we're exposed to, remember, potentially 100,000, from food contact articles, they all act independently. So that's the model of independent action. Now, there's a few research projects that are ongoing. Euromix was mentioned, the EDC mix risk. What their recommendation is to actually assume that these chemicals don't act independently, but to assume that there's dose addition. And then we would take the effects of each chemical and we would add them up. They are saying that should be the new assumption. Of course, we have, this is biology, we always have exceptions from the rule. So we have antagonism, of course. That would be one of the exceptions when chemicals cancel their effects out. That's something that has been documented in some cases. And then, of course, we have the opposite. We have synergy. And that's also been shown. That's been shown in vivo studies where the effects of chemicals are larger than what you would assume them to be by applying dose addition. So there's no clarity in the scientific community as to how to deal with synergy or antagonism right now. So the standard recommendation really is to go with dose addition. And one of the assumptions that has been made, and I think the Euromix project also made this assumption, apply an additional uncertainty factor. It's arbitrary, like most of the uncertainty factors we're using in risk assessment, but it's better than just ignoring this. So this is what's being discussed. And there was a very good commentary article in Science by Andreas Kortenkamp and Michael Faust on this that was published last year. So it's a short read. I recommend having a look at it. Okay, so what my point is, low doses matter. And they matter because we do see increases of non-communicable diseases. And don't take my word for that. Okay, maybe you do have to take my word for that. I was going to show you some data by the World Health Organization, who's finding increases of non-communicable diseases worldwide, not just in the developed countries, but also in the middle and low-income countries. So non-communicable diseases are those diseases that we would call maybe chronic disease. They're not caused by infections, parasites, biological agents, but they're related to all kinds of different factors. Genetics, that's an important one. But our genes haven't changed over the last 50 years, right? That doesn't go so fast. So there's other factors. There's diet, there's physical exercise, sleep, hugely important for health and well-being. But there's also chemicals, and we know that. We know that chemicals can affect health. We know that from dozens and dozens of toxicological studies. And so it kind of seems like a no or low-brainer to assume that by reducing exposures to known hazardous chemicals, we can contribute to prevention of at least some of these chronic diseases, these non-communicable diseases. And that's the hypothesis that I'm making here. And I realize these are multifactorial, right? So it's not just the one silver bullet, but it's something that can help. And why is it important? Well, because first of all, chronic diseases have a huge impact on our economy. We have, well, in Europe, we have healthcare, right, for everyone. Everyone in Switzerland, if you move to Switzerland, like I did many years ago, they force you to document within a week that you've signed up to a healthcare plan. You have to have healthcare, and it's like that in many, many European countries. I'm not sure what the situation in the US is, sorry, I don't want to go there. So, anyway, so it costs all of us. We're in this together, right? We pay for bad health. It has economic impacts, people missing work, and so on and so on. But on top of that, because money isn't everything, right? It also results in impaired quality of life. People are suffering from these diseases. And I once submitted a paper where I argued that we should be looking for chemicals that can contribute to diabetes. And one of the reviewers wrote back to me and said, well, that's a manageable disease, so we shouldn't worry about diabetes. I respectfully Disagree, yeah. I think we do need to care about that. It's our job. If we know about these things, we do need to care about them. Okay, so, and I'm just going to skip over this. The big question is, are there hazardous chemicals in food packaging? And I just want to briefly show a study done by Professor Christina Nerin, who found a surfactant, surfenol, migrating from food-grade plastic packaging to be an endocrine disruptor. There are several other examples there. We've done our own research on this. We've published several lists of known hazardous chemicals that are authorized for use or used in food packaging. We've published reviews where we found chemicals of concern or substances of very high concern, as they're called in Europe, to migrate from food contact articles. So this is a thing. It's real. We see it, it's happening. These are authorized, known hazardous chemicals. So that's kind of low-hanging fruit. We could do something about that. And I have to applaud the American food industry. They have done something about it. Last year, I think exactly a year ago, March last year, they published a list of food packaging considerations listing a whole bunch of substances of very high concern, chemicals of concern, that they do not want to see in their food packaging. That is terrific. And I really appreciate that. So I don't know if anyone here was involved in that, but congratulations. I think you're doing the right thing. Okay, so we have done a bit of work on this. We have developed a database of chemicals that are associated with plastic packaging. We're calling it the CPPDB. So that's the acronym you'll hear a few times. And I also want to point out that this database is not only for food packaging, it's all kinds of plastic packaging. But I'll point out the food relevant aspect. So what did we do? We went to the wonderful CPCAT database of the US EPA, which is a really, really useful resource. Plus we mined the literature and some commercial databases, put together a database of 4,255 chemicals with unique CAS numbers that are likely or possibly used in plastic packaging. And to make it a bit easier, we then split that database into two lists. So the list A are those where we have pretty good evidence that they're used in plastic packaging. List B is possibly. And one of the conclusions we drew from this exercise, which was a lot of hard work, and I want to thank my colleague, Dr. Xenia Groh, who spent many hours putting together this list and occasionally cursing about it, but always very friendly. It's really hard to get this information on use. And Dr. Wember of the EPA mentioned that yesterday already. We really lack this use information. We don't know what all these chemicals that are out there are actually being used for. And that's kind of important if you want to do risk assessment. I guess you agree with me on that. Okay, so what are these chemicals? I'll focus on list A, likely associated with plastic packaging. So these are 902 chemicals. The majority of those, about exactly 788, are also relevant for food contact applications. Okay. We then compiled hazard data, and we said, okay, let's not get into a big argument about your hazard data, my hazard data. Let's go for the globally harmonized system. There's an agreement between many countries in the world to exchange or share hazard data. And so we took this globally harmonized system hazard data. There's quite a lot of it in Europe. We have the CLP regulation. And we extracted those hazard data for the substances in our database. Then we used a method to rank the chemicals according to their hazard properties. And we came up with 63 chemicals that are top hazardous for human health and 68 chemicals that are top hazardous for environmental health. And we also included some other hazard data. You may have heard of the European Chemical Regulation REACH. They have hazard properties of persistence, bioaccumulation, and that's the PBT-PVB data. We included that, and then we also included from UNEP a very good overview report that was published last year compiling EDC classification from many different countries in the world. So interesting here, maybe just to point out, EDCs 35, according to UNEP, that's always limited to the ones that actually have the hazard data, right? But all of those are relevant for food contact. So many of the chemicals that are in our database actually lack hazard data. And just to give you the exact numbers, so we have hazard data for about a quarter of the chemicals in our database on list A. There's less on list B. And about 13% for the environmental hazards. We ranked the chemicals. We came up with a list of 148 top hazardous chemicals. So that list is because they're at the highest rank. And they were overlapping, some of them. And what kind of chemicals were these? So, no big surprise, monomers. They're meant to be reactive. They are hazardous, okay? That's something we can manage. But there's also a couple of additives there. Surfactants, plasticizers, biocides. Big topic as well. So, next, we said, okay, 148 chemicals, too many to look at in detail. Let's prioritize them. And this is a report that we published last year in September, where we did prioritization on the one hand for the environmental risk, on the other hand for the human health risk. And this is not a peer-reviewed report. You can just download it on our website, because this is not really science. This is just us looking at this and saying, okay, this is a case study. You could do it this way, but there's probably 20 or 500 other ways that you could also do it, and you could always argue for this being the right or the wrong way, okay? So this is what we did. We came up with one priority chemical for the environmental risk, which is benzoyl phthalate, BBP, and we were a bit more ambitious with the human health, and we came up with 5 priority chemicals, all of them orthophthalates. And surprise, 2 weeks ago, Tosca released their list of priority chemicals, and all of these 5 are on there as well. So maybe we did something right, or maybe Tosca just copied our report, I don't know. But these seem to be of concern. Also, just a little side note, the EFSA, I guess most of you know EFSA, European Food Safety Authority, they have just published a scientific opinion looking at phthalates, 5 phthalates for application in food contact plastic, and we've got 3 of those on our list. So they don't have the DCHP and the DIBP. They've got 2 others on there. But I won't comment on EFSA's work here. Okay, so what are we doing with this now? I have 5 more minutes? Okay. So Jim asked me to talk a little bit about our ongoing research. I will do that. It's nothing published yet, so I will be a bit coy about it. But we're really interested in understanding the risk assessment for these chemicals. So we've got Dr. Marisol Maffini, who's also here, who's working on that right now. And we hope, together with Professor Leo Tresander, New York University, and we will be presenting the results of our environmental and our human risk assessment in September, when we're holding a public event on this research project. What we're also working on, kind of a follow-up to this work, we want to understand how food contact chemicals are associated with human health outcomes. That's a big, big topic. Specifically, we want to understand which are the ones that are flying under the radar so far. So we've heard a lot about bisphenol A, we've talked a lot about the phthalates, there's the PFAS, the per and polyfluorinated substances. Those are sort of the ones that everyone's always talking about. We want to look beside the lamp. How did you say? Don't look under the lamppost. Yeah, look beyond. So that's what we're doing with this work. So watch that space. We will hopefully soon publish something on this, starting off with a systematic evidence map for documenting all the migration studies, all food contact chemicals that have ever found to migrate from food contact articles. And we've published a protocol for that. I think the link is on one of the slides. So if you're interested, you can come talk to me about that. Okay. One little last challenge before I run out of time. This is a report we did on food packaging in the circular economy. It's a big, big hot topic in Europe. Maybe you've heard of it. Everyone's talking about how can we go circular, and one of the ways to make the transition, it's not the end game. I think that's important to understand. The transition step is to do more recycling. And so we prepared this review, published it last year, looking at the 5 major food contact materials that are used for food packaging and how they perform in recycling and what the common contaminants are and so on. So it's very, very data heavy. It's not a fun and easy read, but I urge you to have a look at it. I think it's very informative. Okay, so just to finish off, I think we've come a long way since 1958, and we have a lot of modern tools. We can understand effects of chemicals on human health so much better today, and so that would be my hope, my wish to you who have to solve these difficult challenges. Please embrace the use of these modern tools that science has given us. We don't use binoculars to study the night sky. We use Hubble telescopes. So that's what we should be doing when we do toxicology. So to finish off, I hope I showed you that some of the chemicals that are used and authorized for food contact articles are known hazardous chemicals. We have more than 10,000 potentially migrating substances. So it's definitely more than just the few that are being studied routinely. And there's a big challenge here because many of the potential migrants lack toxicity and exposure and use data. So it's really impossible actually to do risk assessment. But we have to do risk assessment. We have to assess the risk for each and every single migrating chemical. And so I would say we need to find new approaches to do that. Maybe the substance by substance approach is not going to work for 10,000 chemicals. And with that, I would like to, just put my plug, but Jim already did such a beautiful advertisement for Food Packaging Forum. So we have tons of resources on our website. We have a newsletter that comes by email twice a month. We do webinars. We publish dossiers, which are summaries of different topics. We do peer-reviewed publications. You can find all of that on our website. And you can also find more about what our source of funding is. We live off donations. We're a charitable organization registered under Swiss law. That's the team there, whom I thank for their great work. This is the team for the plastics in chemicals in plastic packaging project. And I also would like to thank MAVA Foundation, who funded this work, and thank all my collaborators. Please save the date for our workshop this year, 24th of October in Zurich. And I know many of you would be terrific speakers, so if you're interested in coming to Zurich, please let me know. I would be very, very happy to host you. Thank you so much.